Section 10.4, this should say up here, Section 10.4. Okay, Section 10.4 student notes. We're going to go through these really quickly. Save you guys as much time as possible. We don't look at that. That's cheating. Okay, so for today, in class we talked about this a little bit. Briefly, we touched on it. Today we're going to explicitly define it, what we call a chord of a circle, a chord of a circle. Okay, and a lot like a chord of the piano starts and ends in a certain place, a chord on a circle also starts and ends on the inside of a circle. Okay, it's kind of a loose way to remember it. Whenever remember in the me blank, you can put whatever you want, but for me, I'm gonna put a segment with its endpoints on the circle. A segment with its endpoints on the circle. Okay, cool. Math defines it very similarly. It's just a segment with its endpoints on the circle. All right, cool. All right, for the next one, this is a recap. This is one we've already done, diameter. I'm going to write a very similar thing. A diameter, excuse me, I meant to say a segment. A segment with, that is not how you spell with. With its endpoints on the circle. And what? And, additionally, like we talked about on 10.1, additionally, its midpoint is C, the center is C. The center. So if I come over here and I draw the center C into this circle, the diameter is the segment that has its ends on both pieces and passes through the center. This guy isn't a diameter. Okay? This guy here isn't a diameter. This guy is a chord. The diameter is a chord by definition. It's a segment with its endpoints on the circle, right? So the diameter is a chord. Let me say something like this. You ever heard a rectangle is not a square, but a square is a rectangle, right? A diameter is a chord. But a chord is not always a diameter. It could be, but it's not always a diameter. Okay, you don't have to write that down. You just gotta think of it. Remember it like this, right? Okay. So if we were in class, we'd be naming these theorems like we did before. But since we're online, I'll be naming them. The first one, we're gonna prove it outright. We're gonna do a big proof. Okay. If chords are congruent, what does that tell us about their corresponding arcs? If chords are congruent, what does that tell us about their corresponding arcs? What can we know about this? What can we know about this? Okay, what if I drew a picture in here? What if I zoom in a little bit? Help you guys see. If I drew a picture like this, I'm going to connect these lines like this. And I'm going to do the same thing over here if it'll stop clipping around. There it goes. Look at that. Not like that. This one right here, okay. Of course, it's not going to want to line up now. All right, so if I'm looking at this, what's special about these lines I just drew? What do we call those? If you're thinking in terms of our definitions, right? These are all radii. Radii. These are all radiuses. These are R, right? R. Okay. Well, this guy is equal. These guys are all equal because they're all the same length. They're all the radius of the circle, right? So they're all the same length. Look at this. Side congruence. I have a triangle with similar parts. So that means these angles are the same, right? That means these angles are the same. And so that means these arcs must be the same. So look at this. Look at this. Just from knowing that two segments are the same, two chords are the same, we can conclude that the arcs are the same. So here's what we're going to do. We're going to prove that real fast, rigorously. All right, so let's kind of start over here. And you guys don't have to erase this. I'm just going to go through it again real quick so we can mark our steps as we go. Okay, the first thing is given, right? So we're going to do given. First thing is given. Segment SH is congruent to segment LR. Okay, Segment SH is congruent to segment LR. That's given. That's the only thing we're given. Okay. Well, the next thing we're going to draw is that all these segments with C in the middle, right? All these segments with C in the middle, notice these aren't necessarily vertical angles, guys. Not necessarily. We haven't drawn them like that, okay? So, what we can see here is we're going to get segment CS is congruent to segment CH is congruent to segment, let's see, what is it? CL is congruent to segment CR, right? And that's just all these radii. Look at this. There's 1, there's 2, there's 3, there's 4, okay? All of them are congruent. Cool. So this is by radii have equal lengths. So radii have equal lengths. That's our reasoning for this, right? Okay. Now I can make a triangle. I can say triangle HCS. Triangle HCS is congruent to triangle triangle RCL, right? Triangle RCL. And that is by what? That's by side congruence. Okay, side congruence. Okay, and then here we have angle SCH, this central angle, angle RCL, so angle SCH is congruent to angle RCL. Alright, and that's by congruent parts of congruent figures are congruent. So CPCFC, congruent parts of congruent figures are congruent. Okay. And now, look at this. This is a theorem we named in class the other day, right? Whenever we figured this out. We actually figured this out if you were here yesterday on Monday, right? So look at this. We're gonna have this length here. These arcs must be equal because their interior angles are equal. Their corresponding angles are equal. So what we're gonna write is arc. This is our final line. Arc SH is congruent to arc RL. So look, there's a lot of steps here. But they're really not that bad, right? These are not that bad steps to make. And this final step is by what? Well, it's by that one theorem, right? We're going to call it the central angle theorem. Central angle theorem. Okay. Very cool. Look how easy that was. Not that bad, right? So now we just got one more theorem, and then we're done. We're done with all these. Okay, so yeah, actually, let's talk about this real quick. The big takeaway from this, from Shirley's theorem, whatever, right? This one is called the congruent chord theorem. Congruent chord theorem. So chords are congruent if and only if their arcs are congruent. So chords are congruent if and only if their corresponding arcs are congruent. Okay. So cool. Now this next theorem has to do with perpendicularity. So if the diameter and a chord are perpendicular, what does that mean? It means it's at 90 degrees, right? What do we know about that chord and its arc? Okay, so here's what we're looking at. We're looking at the diameter and a chord. So here's a diameter that passes through C. Let me get this instead. Here's a diameter that passes through C, right? You guys see this? So it starts at S, goes all the way to C, then goes all the way to R. Okay. This guy, LPY, that's just a chord because he doesn't pass through the center C. Okay. So what can we draw about this? What can we draw? You guys try and do this on your own. I encourage you to pause the video and try and do this on your own. Okay. What we want to know about its chord, this chord LY, we can draw another triangle just like we did last time, right? So I'm going to draw a triangle right here. This is the hypotenuse right here. This triangle right here. And I know this is 90 degrees by supplementary. Okay. So now I know that these two sides, well, let me say this. This side, it's shared. This side is shared, right? Okay. So likewise, this angle is the same. And then what? What are these guys? This is a radius, right? These guys are both radii. Okay, so these guys are the same. These guys are the same length. And now, by HL congruence, so I'm just going to write this down. You don't have to write this down if you don't want to, but just so we can make a note of it. By HL congruence, we know that these pieces are, let me do this in orange instead. This piece right here must be equal to this piece of here by congruent parts of congruent figures are congruent, right? So look at this. Now we've concluded all you need is a 90 degree. All you need is a 90 degree. So if the diameter and chord are perpendicular, then the chord is bisected. The chord is bisected. It's turned into two equal pieces by the diameter, which means that these chords must also be what? They must also be congruent. So now I'm going all the way to 4 tick marks just to make this point. Look at that. Okay, so these guys are also congruent to one another. Look at that. And that's just because these angles, right, these central angles here are going to be congruent. Okay, do you guys see that? So that's another theorem right there. And just to sum it up, right, if the diameter and a chord are perpendicular, then the chord is bisected. The chord is bisected. Excuse me, not that. The chord is bisected by the diameter. By the diameter. Look at that. Okay. Now, a couple of examples really quickly, and then we'll be done. This is our last thing for today. Check this out. What do we know about these guys? This is 90 degrees. So the theorem we just said says what? It says that these guys are congruent, right? These lines are here are congruent. Okay, so I'm just going to set this up algebraically. 2x minus 21. That's that piece. Equals x plus 15. That's that piece. Okay, like terms, move my x to this side. I'm going to get minus x from both sides. I get x is equal to. And if I add 21 to both sides, I'm going to get 36. X is 36. Look at that. One stepper, and you're done. Alright, so for the time being, we are going to skip this one. Okay, I don't know what I was thinking when I set this one up, but this whole page is messed up, so we're going to make a bunch of corrections. But if you guys want to try to solve this last side for the hypotenuse using Pythagorean theorem, you're welcome to. We're not going to do it in this video, though, because it would just take a little bit too long. So if we come over here to this next problem, okay, this problem is supposed to say to find the measure of all these angles. Okay, so what we're going to do is we're going to find C right here. Okay, so this is our center point C. We're going to call it that, right? So that means this angle right here must be 45. This angle must be 45. So this angle must be 45, right? And that's because these guys are actually equal. Okay, so they're have congruent chords because it's bisected by our theorem, right? So that gives us all those angles. And if we had a length of one of these sides, we could figure out using special right triangles the length of these other sides, right? So actually these guys are all equal. Okay, so that's pretty cool. So moving on to this last piece right here. Okay, this side right here, I'm going to white this out. This is supposed to say, on yours guys it says 5, okay, but right here it's supposed to say 4. So I should say 4x, okay? And now, knowing that these guys are congruent, that means these pieces are congruent, right? These pieces are congruent. Maybe you guys can't see that in this color. Let me get a different color. These guys are congruent because these guys are congruent, right? These guys are congruent because these guys are congruent. Cool. Okay, so I'm going to set them up just like I read. They should be equal. They should be equal, so that's what I'm going to do. 5x minus 13 is equal to 4x plus 11. Okay? So if I add 13 to both sides, I'm going to get 5x, right, equals, and on this side I'll get 4x plus 26, right? And then if I subtract 4x from both sides, I'll get just this x is equal to 26. Okay, cool. So x is equal to 26. That would be the measure of both of these sides, right? And then I could use, if I knew another angle, I could figure out the rest of these guys. Okay, so that's pretty much it. This is all you guys need to start working on the worksheet. Go ahead and get started on that. Try and finish it before we come back to class. If you guys have any questions, feel free to talk to me or Mr. Smith. Okay, bring it into class, all that stuff. All right, you guys have fun working on your worksheet.